In an ideal gas, flowing through a nozzle. A shock wave involves an extremely rapid and abrupt change of state. Involves an extremely rapid and abrupt change state. In a normal shock, this change of state takes place across a plane normal to the direction of the flow. Shock. This change of state take place across a plane normal to the direction of the flow. This figure shows a control surface that includes such a sharp normal shock. We can now determine the relations that govern the flow. Assuming a steady state, steady flow, for a steady state, a steady flow, we can write the following relation. With subscript x and y denote the condition upstream and downstream of the shock. Upstream, downstream. Of the shock respectively. Note that no heat or work crosses the control surface. So for the first law, HE plus B HX Vx Hy Vy H0x H0y. Continuity equation. M dot on A rho x Vx rho y Vy. Momentum equation. A M dot Vy minus Vx. Second law, we say that we logarithm equation like the other is its generation and equally for the isentropic process. The energy and continuity equation can be combined to give an equation that when plotted on HS diagram is called the Fano lines. The energy and continuity. First law and energy combination Fano line. Similarly, the momentum and continuity equation can be combined momentum and continuity. Rayleigh line. Both of these lines are shown in this picture. The Fano and Rayleigh line. It can be shown that the point of maximum entropy on each line, point A and B, maximum entropy each line corresponding to Mach equals to 1. The lower part of each line corresponding to supersonic, lower part supersonic, and uppercase subsonic. Subsonic velocity. The 2 points where all three equations are satisfied are point X and Y. Point X and Y as shown in this picture. Three equations are satisfied. Continuity, first law, and second law. X being in the supersonic region and Y in the subsonic region. Since the second law requires that Sy equal for the second law Sy minus Xx in an adiabatic process, we conclude that the normal shock can be proceed only from X to Y. The equation governing normal shock wave will now be developed if we assume constant specific heat we conclude that the equations, the energy equation give us this relation. This is there is no change in stagnation temperature across a normal shock. No change in stagnation temperature across a normal shock. T0x on Tx, we can write this relation. T0y on Ty and substituting into the equation we can obtain Ty on Tx m by the equation of strength, the definition of Mach number, and the relation C equals to KRT. By introducing the continuity equation as follows, we can write continuity, say that RTY Ty on Tx Py on By Px Vx X Mx Kx. square. Combining these equations, these recent equations as shown here, we can obtain the, which involves combining the energy, this equation and equation. The follow lines Py on Px Mx Mx second My square. The momentum and continuity equations can be combined as follows to give the equation of the Rayleigh line. Which give us this relation Px Px plus rho x mx2 cx2 ky, the Rayleigh line, and also we have, can write this relation Px mx L square and Px or for Rayleigh relation we can obtain also this final relation. We say that we have two relations, the Fano and Rayleigh relation, which combining Fano and Rayleigh lines, we can obtain this relation a Mach number at point x square Normal shock function. Table A on page gives the normal shock function, which includes my as a function of mx. Is always subsonic. This table applies to an ideal gas with a value of 4K. Note that mx is always supersonic. And Mach number at pi is subsonic, which agrees with the previous statement that in a normal shock the velocity change from the supersonic to subsonic. These tables also give the pressure, density, temperature, and stagnation ratio across a normal shock as a function of mx. Pressure, density, temperature, and stagnation pressure. These Fano and Riley equations of a state note that there is always a drop in stagnation pressure across a normal shock wave. Always a drop in stagnation pressure across the shock. And an increase in the static pressure. Nozzle and diffuser coefficients is the next section.